All right, so in this chapter, we're going to talk about logic. And by logic, I mean mathematical type logic. And the point of this whole chapter is to get you to think about the words and phrases and how things are used in everyday language and getting into mathematics. All right. So the reason why we're doing this is that logic is important in understanding what people are saying and understanding how the world is working. Okay. And the reason, again, another reason that it's in this book, in this course, is that people get it wrong all the time. People often think, will give bad examples or poor examples of an argument, or to defend something, they will give very poor examples of logic and not reason things all the way through. And we all know examples of those. I'm not going to spend any time on any particular ones. So let's start out with the basic tenets of logic. All right. So a statement is just a sentence that's either true or false. Now, a statement is either true or false. In mathematics, we're not saying it can be either. Okay? It cannot be both true and false. It can't be a little true or a little false. It either is true or it is not. Okay? So here's some statements here. The first one says the door is black. All right? Is that a statement or is that not a statement? Should be pretty clear that no matter what door I'm talking about, it is either true or false. It's black or it's not. Okay? So this first one, the door is black, is a statement. A question like, where are my keys? That's not a true or false. That is not either true or false. So that is not a statement. And a directive like, find your brother, is also not a statement. Obviously, find your brother is an order. So, statements are things that can be either true or false, and can be proved. Tend to think they can be proved true or false. Now, what we're going to do is we're going to talk about a couple of things, and mostly we're going to focus on some of the different words we deal with. But we're going to focus on two main aspects. One of them is negating statements, or negating any sort of phrase. And when I say negation, I'm just saying it changes a true statement to a false one, and vice versa. So let's look at a couple examples. If we were to negate, the window is open. All right, the window is open as a statement. So the negation of that is the window is not open. All right. Now notice something. If I were to say the door is open, that's not negating the window is open, right? The only negation of the window is open is saying the window is not open. To say Detroit is the capital of Michigan, well, the negation of that is that Detroit is not the capital of Michigan. Okay? Now, some people get this wrong. Oftentimes, people will say, phrases like, well, Lansing is the capital of Michigan. That's not negating Detroit is the capital of Michigan. That doesn't negate the statement. Okay? Obviously, we all know that there's one capital, but the negation of the statement, Detroit is the capital, is Detroit is not the capital. Right? if we say something like, now in the previous two, in both cases, we did nots. So what if we have the glass is not empty? Well, the negation of a statement like that is saying that the glass is empty. And there you go. So negating statements should be a fairly straightforward thing. You're going to have to do those. You're going to have to negate statements and tell me which things are statements and which are not on quizzes and tests and things of that nature. Now what we're going to do to these statements is we're going to add quantifiers. Okay? And by quantifiers, I mean things like all or some or none. Right? And these are different quantifiers, and they mean very different things. To say all men are something is very different than saying some men are whatever. And when we say quantified statements, that just means statements with quantifiers in them. Now I said we're going to look at negating stuff, but the other thing that we're going to look at a lot in this chapter is equivalence. And so we're going to start out looking at equivalence. Obviously, two statements are equivalent if they mean the same thing. All right. So if we're using quantifiers and we have a statement like saying, well, let's just call A and B something. All A are B. Okay. The equivalent to that is saying that there are no A that are not B. Now, oftentimes it's useful to think of this in terms of set theory, right? So let me just draw a Venn diagram here. If I were to say everything in set A is in set B, right? We have that picture. So set A is here. So the smaller, essentially, subset. And basically, if we say all A are B, we're saying everything inside of set A is also inside of set B. Okay? Now look at the equivalent statement. The equivalent statement says there are no A that are not B. In other words, there's nothing outside of A. Excuse me, there's nothing in A that's outside of B. All right? Everything in A is in B is the same as saying that there's nothing in A that's outside of B. Okay? And a lot of times what we can do is we can use Venn diagrams and set logic, set theory, to understand better what these statements are saying. So I want you to try these next three. Try pausing the tape. Try drawing these things in terms of sets, in terms of Venn diagrams, and see if it makes sense that saying some A are B is equivalent to saying that there is at least one A that is in B. And no A are B is equivalent to saying all A are not B. All right, so push pause. All right, so coming back to this, if you draw a set about some A are B, I'll draw it over here. What we're essentially saying is, inside the circle of A, there are some things in here, which are also in B. In other words, we're saying in set language, A and B intersect, have a non-empty intersection. Okay? And notice it doesn't tell us how many things are in the intersection. And so it just, some A or B tells us that there's at least one thing here, which is exactly this statement. There is at least one A inside of B. And to say no A or B, what that's saying is in terms of Venn diagrams. We have an A here, and nothing inside of there is inside of B. In other words, there's no overlap. It's equivalent to saying all A, everything in here, is outside of B, or not B. Okay. Some A or not B, well, all we're saying is some A or not B. A, B. Is that there's things in A which are not in B. In other words, there's things in this region here. Okay? And that's equivalent to saying that not all A are B. So there's not everything in A is inside of B. There's things that are in A but not in B. Alright, so this is what we just did. We examined the Venn diagram. I did this on the previous slide. So, but I want you to be able to draw this, okay, on a test or something. So when I say all A are B, you're saying everything in A is inside of B. Okay? There are no A that are not B. In other words, there's no A outside of the circle of B. Okay? And the same thing, I drew this on the previous slides, so I'm going to skip this. Now here's where it gets interesting, because we want to negate things. Alright, remember I said the two things that we're going to focus on a lot in this chapter are equivalence and negation. What things mean the same, what things mean the negative. Right. So take a statement like all A are B. What that means is everything in A is inside of B. Now if I negate that, what I really have to do, here's how I think of it, is I think of it as proving it false. If I said all math teachers are males, how could you prove that false? Well, you'd have to find a math teacher which is female. And again, fairly easy to do. So notice that the negation of the statement is not saying that no math teachers are female. The negation is saying I can find at least one that's not. So in other words, the negation is saying I can find something in A that's outside of B. In other words, some A are not B. There are things in A that are not in B. And then with these quantifiers, if I look at the next example here, let's see if I can draw this. Maybe not real well. It says some A are B. In other words, we have things in the intersection. Now, to negate this, we'd have to prove that there's nothing in the intersection. In other words, there's no A is inside of B. The intersection is empty. Okay. Notice that that's proving something false. So a lot of times when we get into this negation stuff, think of saying, well, how would I prove it false? If I said all math teachers are males, if I to prove that statement false, you just need to find one math teacher that's not a male. If I said some math teachers are males, to prove that wrong, you'd have to prove that no math teachers are male. Right? So I want you to push pause and find the negation of these three statements. All right. Now, to negate all men are pigs, if I was trying to prove this false, I just need to find one, or at least one. So I'll say some men are not pigs. Notice again, we're changing all to some. If I say some doctors are stupid, all right, what we're saying is, to negate that, we say no doctors are stupid. Okay. To say no pigs are gray, well, the negation of that should be some pigs are gray. All right. Notice, by the way, how the second and the third are related, right? The sum A R B is the negation of no A R B. Okay? So we had the same sentence structure in reverse. No doctors are stupid, no pigs are gray. All right? Some pigs are gray, some doctors are stupid. Okay? So they're negatives of each other. And that would go for the following: some men are not pigs, all men are pigs. You can start out with this statement, and if I was to negate it, it would negate to that one. Now, what I want to mention this, we're not going to spend lots of time on the symbolic stuff in this class because that's not the focus. But I do want to mention that if I have a statement, a lot of times it'll be labeled with like a P or a Q. And if I'm negating that, they put a tilde in front of that. Right? So a statement might be P, the negation would be tilde in front with a P. Okay, like I said, we're not going to deal with that a whole lot in this chapter, but if you read somewhere, if you're talking about symbolic logic in another math class, I want you to have at least seen that.